One thing we're going to introduce is the Ka. Today you have an acidic solution. Either it's a strong acid or weak acid. In general, you can actually write it, your acid Ha dissolving produce protons and its conjugated base. Then if you write out the equilibrium equation for this equation, then you know on the top is actually your product, right? So it's actually H3O plus times your A minus. At the bottom is only your HA, right? Because the substance existing in the pure liquid or pure solid form did not goes into your equation. So here you can actually write this H3O plus and H plus. Okay, then you get this. If today you have higher equilibrium constant, Ka, you're going to get higher concentration of proton. Therefore, it will be more acidic. Using the same concept, you can write the same thing for your base, BOH. It's going to interact with your water, produce B plus, which is the conjugate acid of your base, plus OH minus. Then you can actually write out the equivalent constant equation for this. Again, if you have a larger Kb, you are going to have high concentration of OH minus. That make the solution more basic. In other words, the Ka and Kb is an indication to tell you the relative strength of your acid and base. So remember, we're talking about these rules in the very beginning of the chapter that you can use to judge the relative acidity or basicity of a substance. There are actually some limitations. So for the rule number 2, you need to actually at the same column or at the same row, then you can apply the rule. But if they are not on the same column or on the same row, the easiest way is actually look at the Ka. The larger the Ka, the stronger acid. The larger the Kb, the stronger base. So this is actually another way to actually tell the relative acidity or basicity. This is actually a Ka table of many different substances, which you can find the things in your textbook. If you look at Ka, you will see some of them did not actually have any numbers. Things you see below all the way to here, right above your water. You can see the Ka is ranged from 1 to 10 to the negative 13. So all these things is weak acid. So the Ka range actually from 1 to 10 to a negative 13. All the things is actually so-called a weak acid. All the things above, strong acid. So how many strong acids we have? What did I say in the very beginning? 7, right? So if you look at this, there are actually 7 acids, but it's slightly different because here I replaced this guy with Hi. But including that, okay, you can have 8 acids. So these are the acids that you need to memorize. Here you can see that the Ka goes from 1 to 10 to the negative 13. On the top is a stronger, at the bottom is actually weaker weak acid. If you have dichloroacetic acid versus neutral acid, which one is actually stronger acid? And I give you the Ka values. The one with larger Ka value will be the stronger acid. So once you know the Ka, you can also calculate the pKa. You take negative log of that, right? Negative log of Ka will give you the pKa. Okay, if you see a pKa is actually negative, means actually it's actually super strong acid. Water Ka is actually 10 to the negative 14 or equals to just 14. Okay, so this is actually a special case that you also need to memorize. To summarize this slide, 2 things. First, do you need to memorize this table? Don't, but you need to know how to read the table. Second thing, you need to know how to use Ka to judge the relative acid strength. Today I give you a serious substance and provide the corresponding Ka. You need to know how to actually arrange the relative acid strength of all of them. Basically to find the one with the biggest Ka, strongest acid. If today you have a strong acid, how do you calculate the pH? One thing special about the strong acid or strong base is really this. Once you throw them into the water, they will dissociate 100%. They are going to have very big Ka. In this case, we use HCl as an example. Okay, so when you see these questions, calculate the pH of 0.1 m and 1 times 10 to the negative 10 m. HCl aqueous solution. So HCl is actually a strong acid, then you should know that it's going to be 100% dissociation. HCl, once they dissolve, it produces H plus and the Cl minus. Initially, you have 0.1 m. Okay, it haven't dissolved yet, so you know you don't have H plus, you don't have Cl minus. Then once it starts to dissociate, it will dissociate fully, right? That's what it means by 100%. That means actually you're going to completely consume your reactant and form your product. So once you reach equilibrium, you don't have HCl existing in your solution. What you have is actually 0.1 m H plus and 0.1 m Cl minus. To calculate pH, all you need is actually the proton concentration, right? Because you know the pH of the solution is equal to negative log of your proton concentration. Okay, since you know the proton concentration is equals to 0.1, therefore you know your pH will simply equals to 1. Number 2, what if today you have 1 times 10 to the negative 10 m HCl? So what you do is you replace this one. You want to do 1 times 10 to the negative 10, right? And you know it's strong acid, therefore it's going to minus 1 times 10 to the negative 10, produce 1 times 10 to the negative 10, 1 times 10 to the negative 10. So once you reach equilibrium, okay, you're going to produce 1 times 10 to the negative 10 of acid of H plus and 1 times 10 to the negative 10 Cl minus. So if you calculate your pH, it's going to equal to negative log 1 times 10 to the negative 10. That gives you a value of 10. Is this correct? What is HCl? Strong acid. Throw into water. What is the pH you will expect? Lower than 7. What's the number you got here? Something's wrong, right? What does this mean? What it really means is actually, so you are throwing a very, 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 very tiny amount of HCl into water, and you will dissociate 100%. These are all correct. But because the concentration of strong acid you add in is in such small amount, then your water actually get into play. Remember we say if you have H2O, it can dissolve become H plus and OH minus. The Kw is equals to 10 to the negative 14. If you do this calculation, we know the proton concentration and the OH minus concentration is 10 to the negative 7, right? The intrinsic proton concentration inside your water is 10 to the negative 7. This number is actually higher than the proton concentration generated from your very dilute acid, right? So therefore, you add in the amount is so little, your water is actually become the dominant species of your solution. If you throw in this little amount, even though it dissociates 100%, they only produce lead amount of H plus, right? Which is actually way smaller than the proton produced by your water. Therefore, the pH of less solution will be the pH of your water. This is actually not right, okay? So for this one, okay, because the proton concentration coming from your HCl is way smaller than the proton concentration coming from your water. Therefore, the pH is going to equal to 7. Every time when you say the pH of some acid solution, make sure your pH is actually less than 7. If it is not, it has to be 7. Okay, this is a little bit tricky questions you want to pay attention to so you don't actually make mistake. The take-home message for the strong acid case is we want to calculate the proton concentration of a strong acid. The proton concentration will basically equals to the acid concentration provided inside your questions. How about a weak acid? So we give you another example. Calculate the pH and percent dissociation of 1N acetic acid, where it gives you the Ka of this value. Okay, every time you see in the question it specifies the Ka, what it really means you're having actually weak acid. Because strong acid, they don't need Ka. It's 100% dissociation. Even though it's weak acid, right? It's acid, so you know pH has to smaller than 7. Your Ka is 1.8 times 10 to the negative 5. Once you see these things, what should go into your mind? Your Ka is smaller than 10 to the negative 4. So you're going to use what? Small x approximation. You can actually write out your chemical equation. CH3COOH is going to produce protons plus CH3COO minus. This is actually the conjugate base of your acid. Then do the ice table. So for your acetic acid, the initial concentration is what? 1 m. So that's 1 here, 0 here, 0 here. And then since it's going to change, so you know minus x, from x, x. Once you reach equilibrium, you add these two up. So you have 1 minus x for your acetic acid, x for your proton, x for the conjugate base. So now you need to actually use your equilibrium constant K to solve for your x, which we know the K is going to become H plus concentration times the CH3COO minus concentration divided by CH3COOH, which is going to equals to, that is actually H plus, right? So it's X. That is actually your CH3COO minus, which is X. At the bottom is actually your CH3COOH concentration at equilibrium. So you know you're going to have x squared 1 minus x for your K, right? And your K is 1.8 times 10 to the negative 5, right? Small x approximation comes in. So you know this guy is going to equivalent to x squared. At the bottom, it will become just 1. Okay, then equals to 1.8 times 10 to the negative 5. So therefore, your x is going to be the square root of 1.8 times 10 to the negative 5 multiply the concentration of your acid. So that 1 is actually the concentration of your acid. Once you do this, you know your x is going to equals to 4.2 times 10 to the negative 3 m. So that's the number you're going to get, which we know your x is actually equals to the concentration of your H plus and equals to the concentration of your conjugate base. Then we can calculate our pH using negative log of proton concentration. That gives you negative log 4.2 times 10 to the negative third. Okay, then you're going to get a number of 2.38. Okay, another thing he asks is actually the percent dissociation. So the percent dissociation will be your proton concentration at equilibrium divided by your acid concentration in the beginning, multiply 100%. So proton concentration is actually 4.2 times 10 to the negative third. Original concentration of your acid is actually 1 m. Then you will get a number of 0.42% dissociation. Okay, let me say actually only 0.24% of your acid dissociate and produce the H plus. So that is the way you answer the pH as well as the percent dissociation. If you do these things when you are doing your exam, you will never be able to finish in a given time. Okay, so what should you actually memorize? So if you look at these things carefully, for the weak acid, that means actually small x approximation always valid. So if that is the case, the general form you're going to write for your equilibrium constant is this, right? But because you can always use small x approximation, therefore, it goes back to here. So once you know it goes back to here, then you can actually calculate your x equals to the square root of this, which is actually your Ka. This is actually your initial weak acid concentration. Then you take the square root of that, that's going to give you a proton concentration. So the things I want you to memorize is this. Proton concentration of weak acid is going to equals to the square root of your Ka times your initial acid concentration. So with these things in mind, let's relook at this question. You have 0.1 N acetic acid with Ka equals to 1.8 times 10 to the negative 5. What is the proton concentration? Once you see this, the things that come to your mind is actually, okay, I have what? I have weak acid. Therefore, the proton concentration can be calculated through this equation. Plug in the numbers, then you got the proton concentration. You take the negative log of that, you got your pH. So 2 lines, get the answers. This will actually speed up your calculation a lot, okay, because you don't need to go through all these salt experiment anymore.